Okay, well, hello everyone. In this video, I wanted to make an explanation and also some examples in Python, in particular using Jupyter Notebooks, how you can perform cross-validation and why we are interested in performing this type of validation when feeding a machine learning, a statistical learning, or data-driven model. Well, the idea of cross-validation is that we have the whole data set, no? For example, here we have a data set, no, that is represented by these squares, and we are dividing this data set into two main parts. We have a training fold and a validation fold. No, that is the the partition that we are proposing. And the idea is that we will be using the training fold of the data set in order to feed a model, not to train an algorithm based on data. And we will left the validation fold to evaluate the performance of our model that is represented by the blue square that we have in this section. But we call it cross-validation because we can repeat this process many times. And other way in which we can name cross-validation is k-fold cross-validation. And the idea of k-fold cross-validation is to say, okay, I will be splitting the data set into 5 sections, no, into 5 parts, where I will be using 4 parts of this data set for training the model, and I will left one for validating. And I will be interchanging the model. I will be using other parts of the data for training, and I will left the other side for validating. And I will be switching the training and validation folds many, many times. And the idea is that each time I switch the training and validation folds, I will be using the validation fold to make an estimation, no? To make a prediction, and I will compute the performance of the model on the validation set. So in each iteration of this process of training and validating the model by using different subsets of the data, I will be computing the performance on the blue square, that is the data set used for validation, and I will be repeating this process many, many times. And at the end, I will be averaging the results. And in this way, I can have an estimate of the performance of the model that is more reliable. And this is crucial because if you use all the data set for training the model, you can have an overestimate of the model performance, okay? Because you are allowing the model to see the whole data set, but you are not evaluating the model and see how it performs when it's working with samples or data that it has not been seen before by the model. So this is one of the crucial techniques that we have in machine learning to estimate the performance of a model. And well, in particular, we have like a variant of cross-validation that is called stratified cross-validation. And the usefulness of stratified cross-validation is that it can give you a better estimate of the performance of the model when you have an unbalanced dataset, no, or imbalanced dataset. That means that you have a class that is more represented than the other one. So a stratification allows to take samples from the original distribution of each class to be maintained across each fold. What is the meaning of that? What is the meaning of maintaining the distribution of the classes for each fold in the cross-validation process? Well, for example, if your original dataset has 80% of class 0 and 20% of class 1, your folds will reflect the same proportion. Okay, that means that each cross-validation fold will maintain this proportion between 80% of class 0 and 20% of class 1. And this allows us to have a better estimate and a reliable metric of the performance of the model. And well, another thing to take into account is that okay, we can perform this cross-validation process, but we need to compute certain metrics or certain performance. How can we compute that performance? Well, we can use a technique or a matrix that is called the confusion matrix. And based on this confusion matrix, we can compute different metrics. For example, one of the most common ones is accuracy. That is basically, for example, if you are dealing with a binary classification problem, that basically means detecting the absence or the presence of something. Well, we will be taking the true positives, that is, the samples that we correctly classify that are actually positives, plus the true negatives, that is, the samples that we correctly classify as negatives when they are actually negatives. And we divide that by the true negatives plus the true positives plus the false positives. False positives means samples that we classify as positive when they are actually negative or are actually from the opposite class. And also we have the false negatives that are the negatives that we classify as negatives when they are actually positive. So this is like the average of the true positives plus true negatives of the model. But the problem is that the accuracy is biased because we cannot have information related to how well the model is performing for the positive and the negative class in particular, because basically it's aggregating the true positive plus true negatives. And for that purpose, we have, in the particular case of the positive class, two metrics that are called the recall, also called sensitivity, and also we have the precision. Um, well, for the true positives, as I mentioned before, we have the recall. And you can compute the recall by taking the true positives and you divide that by the true positives plus the false negatives. And in the precision, it's a very similar formula, but you need to take the true positives and you divide that by the true positives plus the false negatives. The difference between the computation of the precision and recall is that we are considering one the false positives and the other one the false negatives. I will deepen into the discussion of what is the interpretation of these two metrics, but only to close this presentation or this slide, I also wanted to show you that we have an aggregated metric that is called the F1 score. The F1 score is basically computing the multiplication between the precision and recall. We multiply also that by 2, and we divide all that by the precision plus recall. This is basically like, oh, they call it like the harmonic mean between the precision and recall. And it's basically an aggregate metric that tells us about how well the model is performing by considering these two metrics. And well, in the case of the negative class, we have the specificity that is basically taking the true negatives divided by the true negatives plus the false positives, and the negative predictive value that is taking the true positives and divided by the true negatives plus the false negatives. And well, I will discuss later in another video what are the metrics related to the negative class. Um, and I will deep in and I will show you some examples in how you can compute this precision and recall using Python. And also what is the trade-off between these two metrics, because as a matter of fact, if you increase the recall, well, you can also affect the precision of the model. Okay, there is a trade-off between these two metrics related to the true positives. Okay. So before we go into the Python code, I also wanted to clarify what is the difference between the precision and recall. In the case of precision, remember that the precision is taking into account the false positives. And the question that it tries to answer is, of the ones of the samples that I predicted as positive, how many were correct? Okay. In other words, if all the samples that I predicted as positive, how much I am avoiding the false positives. No, we want to avoid that. So the precision is a metric that is telling us about of all the samples that I classify as positive, how much of them were correct, no? And in the recall, is asking another question: is of the actual positives, how many did I find? Okay, of the actual positives, how many did I find? And to understand that, also we need to go back to the equation, no? The recall is basically taking the true positives and divided by the true positives plus the false negatives. So the question is, how many did I find? No? How many of these true positives I identify? No? And how much I am avoiding the false negatives? Okay, we want to reduce, in the case of the recall, we want to reduce as much as we can the presence of false negatives in our predictions. Okay, so we want to avoid that. Okay? That's why it is asking, okay, of the actual positives, how many did I find? Okay. So let's go to the Python code in order to illustrate this. Okay. So, well, in a previous video, I trained, well, just to recall, we were working with the MNES dataset, and we were using a stochastic gradient descent classifier. We saw that we can import that stochastic gradient descent classifier using this library from scikit-learn. And well, we can make predictions with this classifier. Here I wanted to show you a code, a manual code, that you can use to perform a stratified cross validation. To perform a stratified cross validation, well, again, you need to use scikit-learn.model underscore selection, and you need to import the stratify k-fold function. And well, based on that, you need to create basically what the stratified fold cross validation will be doing is to generate train and test sets of the data set according to the number of partitions that we define. This is to generate the k-fold in the cross-validation process. Remember that in a stratified cross-validation, the distribution or the proportion of the classes will be maintained across all folds. And also to maintain reproducibility, we are setting the random state to a fixed value. And well, once we have defined an object that we can use in order to split the dataset into stratified folds. To do that, we are basically using a for loop to extract the indexes for the training and test sets. In this case, the test index is referring to the validation fold in the cross-validation process. And well, we are taking this function that will give us the indexes across this for loop. Also notice that in the for loop, I am generating a clone of the original stochastic gradient descent classifier that we fit previously. To do that, I am using this function from scikit-learn.base that is called a clone. So I am making a clone of the classifier. Afterwards, I am taking the train index according to the iteration in the for loop in order to extract the indexes from the training data that I will be using to feed the model. And I am doing a similar process for the test indexes and extract samples from the test sets. And I am using the clone of the classifier to feed the model. Once I have feed the model, I predict with the model. And after that, I make the prediction. I compare my predictions with the actual results or the true results. And finally, I am adding the results and then divide that by the length of the predictions. Okay, and this will give you a metric that is comparable to the accuracy that we discussed previously, because we are basically computing how well we are computing both the true positives and true negatives of the dataset, and then we are dividing by the rest of the samples. And this is the result of accuracy. It's a manual process that we can make. I will be running this code. It will take a while because one of the problems of using cross validation is that since you need to train and validate the model k times, no, depending on the number of faults that you define, well, you will need to perform that iteration many times, that estimation, and that takes a lot of computational power, no? And how much time you spend on doing this depends mainly on the hardware characteristics of your computer. Here I am using a very slow computer. It's a ThinkBook from Lenovo, so it's not too powerful. It's one of the basic models, and the progress processor is not so good. But this is only for illustration purposes. Now we are working with um, very simple, no, to put it in a way, very simple classifiers, no, or very simple examples. Okay. So as you can see here in my Jupyter notebook, we are predicting these results, no, in terms of accuracy. And well, since I defined 5-fold cross-validation faults, well, this is the result of the first evaluation. It's taking a little bit of time. So while this thing starts or continue running, I also wanted to explain, meanwhile, another way in which you can perform this stratified cross-validation process. And the good thing is that we already have in scikit-learn a function that is called crossval score. So you can import that function by using scikit-learn.model underscore evaluation, and we can import the cross-validation score. And here you need to define the model that you want, the training and test sets, and also how many faults you want to use. Another thing is that you can also define the stratified cross-validation process. So to do that, one way to enable that option is to in this option that is called CV, you need to define the stratify fault object, that is this one, into this option, and automatically this function will perform that stratify cross validation. Okay, so you don't need to make that by hand, no? Or by using this code, because you can use this function, this already built-in function that scikit-learn has, in order to perform both a simple cross validation or a stratified cross validation. And also you can print here which metric you are evaluating, the accuracy or the precision recall. It depends mainly on what are the metric that has more relevance for your problem. As you can see, well, this thing is continued to evaluating. It has spent like 3 minutes working with this. But well, this is basically the way, in which we can perform cross-validation. And well, before we continue, one of the things that we need to take into account, and that why we need other metrics like the precision and recall, is that, as I mentioned before, the accuracy is a bias metric because it's basically considering both the true positives and true negatives and averaging the results. But this metric is biased because we don't know precisely how well we are doing for the positive class or the negative class. And this is important because sometimes maybe the classifier is not working as expected. Maybe it's making predictions by chance, okay? And to illustrate these points, what I did in this section was to train a dummy classifier. Okay. And before we move to the dummy classifier, here you can see that we already have finished this K-fold cross-validation process. As you can see, we have here the accuracy results of each fold. It takes like around 4 minutes to compute all of this process. And well, I also wanted to show you while I'm explaining this dummy classifier, I will be running the function cross-val score to compute these metrics, but by taking advantage of this built-in function that we have. Okay, so this dummy classifier, in order to generate a dummy classifier, we do need to import the scikit-learn.base import base estimation. And well, we are defining here a class here in Python that is named never5 classifier. The reason of this name is that, well, the model is performing a binary classification. Basically, we are trying to detect the presence of a 5 or its absence. No, we want to only detect the number 5 from the dataset. And well, we have two functions. No, we have a function that is only passing the information. Okay, it's not doing anything. No, this fit function is basically returning the nothing. Okay, and we are doing this because we are trying to see how well this already trained model is doing, um, compared to a model that is doing nothing. Okay. And also we have another function that is called predict. Here you can see that when we are calling this function predict, we are returning zeros according to the length of the input. Okay, and this function is returning a true or a false depending of the length of the model. So afterwards, you can see that, well, according to this, since here we're defining a numpy array of zeros, we will have always false. No? This means that we are not, all the inputs will not be classified as fives. Okay, will be classified as something else. And this is set a priori. Okay, automatically the model will say, okay, this is not a 5. So again, we can compute the cross-validation score. And you will see, I already printed the results in the section. Well, you will see that this model that is doing nothing is making a very good estimate of the accuracy. And that is a consequence of the fact that we have a lot of true negatives in the data set, no? Or negative samples, and a very small proportion of true positives in the samples, or samples that are actually positive. And this is why we say that the accuracy is biased, because it may be biased by the majority class. Maybe the model is not doing anything, no, or is overrepresenting certain class of the data set that we want to classify. And and this is basically demonstrated by this base estimator, no, that is doing nothing more, returning zeros, okay, or returning or telling us, okay, you don't have any 5 in your data set or in your prediction, or you're in your test set predictions, or validation set predictions. And that is why we will need to compute these confusion metrics, because based on these confusion metrics, we can compute these metrics like the specificity, the sensitivity, the recall, the negative predictive value, and so on. So if you want to compute these confusion metrics, well, again, you need to use a function from scikit-learn.model selection that is called cross-validation predict. You need to call that function. You need to define first your model, and then you need to define the training data and your and your and your target training data. You make the prediction, and then based on that, we can call the predictions that you made and compare that with the actual training data. And based on that, you can compute the confusion metrics. Here I already printed the confusion metrics of this model. Here we have that and we have here the this point, only to illustrate this first element is the true negatives. These are the true positives. These are the false positives, and these are um, the false negatives. Okay. In particular, we are interested in that this diagonal line has all the values, and we get values closer to zero in the values that are out of the diagonal of the confusion matrix. Okay, that means that we are reducing the presence of false positives and the presence of false negatives in the data set. And well, here, well, you can see that it takes a lot of time to use this cross-validation fold using cross-validation, well, to compute cross-validation automatically, but here we have already printed the results. And in fact, if you compared the results that we obtain with this function and the function that we use or that in which we implement the stratified cross-validation by hand, well, they're basically the same. Here I am computing or defining the dummy classifier, and here I will be computing the results of performing cross-validation with the dummy classifier. You will notice again that the accuracy is relatively high. And well, if we use now, we compute here the confusion matrix that I showed previously, you will see that um, we can compute the confusion metrics by using the predictions of the model and comparing that predictions with the actual class. And what I was explaining previously is that here the first value is the true negatives, this is the true positives, these are the false positives, and these are the false negatives. And we want a classifier that push these values in, that are the values that are out of the diagonal to zero. And we want that all the values are in place in the diagonal line because there are the predictions that we are making correctly for both the positive flash and the negative flash. And well, here what I'm showing you is what happened when you take your predictions well, you make your actual predictions from the model equal to the predictions in your data, no? Or the predictions from the training data or the target data. And you will see that, well, this is like cheating because I am using as predictions the actual targets, okay? And there is a problem because I am cheating, no? Because but this is only for illustrating that, well, if you make perfect predictions, you will have these true negatives and true positives correctly classified always. No? And well, based on these confusion metrics, we can compute the metrics that we discussed previously. Here in scikit-learn.metrics, we have three functions that can help us to compute the precision, the recall, and the F1 score of a classifier. Basically, you need to call the function, you need to take the actual predictions from your data set and the predictions that were, well, the actual labels of your data set. And also in the second argument, you need to take into account the predictions that your model make. And here I am printing the precision, the recall, and the F1 score for each of the classifiers. Here you can see that we are having a very high precision. That means that we are reducing the false positives on our prediction. But the recall, as you can see, we have a lower value. That means that the true negatives are higher, no? And that means that we are not, how can I put it into, well, let me go back. Sorry, in the recall, the false negatives are higher. That means that there are certain positive samples that we are not currently classifying. Okay. And well, the F1 score is basically computing the harmonic mean between the precision and the recall. And well, this is the way in which you can compute that using um, scikit-learn. Okay. So I hope this video is helpful for you. I will be uploading these codes into a GitHub repository in order for you to see them later. That's all for my part, and see you later.